Okay, guys, welcome. Today we're going to talk about systems of ODEs as they appear in models for engineering. So what we're going to do is we're going to go through two examples that show the importance of using a system of ODEs in some models of, models in engineering. And then we'll talk about an important skill that will be needed moving forward regarding systems of ODEs. Okay, now the first example that we're going to look at is where we have a mixing problem, but we're going to have two separate tanks here. So sort of the natural motivation here, I believe previously we had done a mixing problem with one tank, so that was solving an ODE. But now since we have two tanks, we're going to model this by two separate ODEs, which we'll call Y1 of T and Y2 of T to represent tank 1 and tank 2 respectively. Now, we're told that both tanks initially contain 100 gallons of water. So, of course, we have 100 gallons here, 100 gallons here. But we're told that the water in T1 is pure, at least to start. But in tank 2, we have 150 pounds of fertilizer dissolved. Okay, so we're going to circulate the liquid between these two tanks, and we're going to do this at a rate of 2 gallons per minute. And we're going to assume that we are constantly stirring the mixture just so that we don't have any sort of heterogeneous solution. We're just going to assume that the mixture is completely uniform. And of course, this is going to lead to a change of the amount in fertilizer in each of them. Of course, tank 2 will be losing fertilizer as time moves on, and tank 1 will be gaining fertilizer. Now, the question is, we want to know how long should we let the liquid circulate so that T1 will contain at least half as much fertilizer as there will be left in tank 2. So what we're essentially going to be looking at is a graph where we have this sort of situation occurring, right? So the amount in tank 1, this Y1, it would of course be tank 1, is going to increase to a certain point, and in tank 2 will decrease to a certain point, right? So we'll sort of derive this, and we'll see where all of this stuff comes from. So of course, the first thing we want to do is we want to set up the model. Now, just as before, when we looked at this for the one tank version, when we come up with our derivative, our rate of change, that's going to be basically the amount coming in and then subtract the outflow, the amount coming out. And of course, we'll do the same thing for Y2. All right, now again, remember that throughout, the Y1 is tank 1, which is initially pure, and that Y2 is tank 2, which is initially with the 150 pounds of fertilizer. Okay, now in our Y1 tank, what's coming in? Well, we have 2 out of 100 gallons. So this is the 2 gallon per minute. And of course, we're starting with 100 gallons. All right, so that's where you're sort of getting the 2 over 100 there. And of course, this is being drawn from Y2, right? If you're looking at Y1, you have water coming in from Y2, and at the same rate, we have water going out, so same, but leaving Y1. And then, of course, Y2 will just be the opposite version of that. That's where you have water coming in from tank Y1, and you have water leaving from the current tank, which is Y2 in this case. So if we wanted to write this as a system of ODEs, we have that Y1 prime is given by negative 0.2 Y1 plus 0.02 Y2. And in Y2, we have Y2 prime which is equal to 0.02y1 minus 0.02y2. Now, in most settings, it's going to be, and let me just show you the extension of sort of the unit analysis here. I sort of started to write that out, but I didn't finish. So again, we're letting this y1 and y2 being the amount of fertilizer. All right, so that is important. All right, and y2 is also the same. So for example, I'll just show this for one sort of part of this. You have 2 gallons per minute, and this is in terms of the entire mixture, right? So this is the water and fertilizer mixture. Right. Now, of course, how many gallons is in there? Well, it's whatever is in Y2, right? Because it's going to be changing with respect to time. It's going to be whatever Y2 is in pounds per 100 gallons. All right. So, of course, what happens, your gallons cancel out, and this is represented as Y2, I should say 2Y2 over 100 pounds per minute. Right. And you could do sort of a similar unit analysis for all of those other quantities too, but that's sort of where that's coming from. I wanted to make sure that I explain that without moving forward. Okay, but anyway, so back to our system, right? So we said that our system could be given by these pair of ODEs here. And of course, it's going to be nice to represent this as a matrix equation. So if we let a y vector be our sort of our solution vector here, and we consider a coefficient matrix A, then we can say that our ODE is really a matrix equation where we have y prime, which is, again, so out here, this looks something like this. We have y1 prime, y2 prime is equal to our coefficient matrix A times y1 and y2, right? And of course, your coefficient matrix A is just going to be given by this. All right, so now we've set up the model. Okay, so our model is represented by a matrix equation. Now, to find the general solution, we're going to sort of solve this in a similar way as we would for just the single equation case, right? So we're going to assume that our solution vector y is some sort of vector x times e to the lambda t. So that way our y prime is going to be, once we take the derivative of the e term, the lambda will come out front, multiplied by the x term. But again, we know that for any matrix equation, if we have lambda x, that's the same as a times x. And now if we divide both sides of this equation by e to the lambda t, we're getting an eigenvalue problem, right? So we have our coefficient matrix A times some vector x is equal to lambda times that same vector x. Right, so what does this mean? This means we need to find the eigenvalues and eigenvectors of our coefficient matrix A. Right, so if we do that, what we need to do is we need to find the determinant of our coefficient matrix minus lambdas on the diagonal. So if we find that determinant, you'll eventually get that you can factor this as lambda times lambda plus 0.04, which of course is going to give you 2 eigenvalues, one of course being 0, and the other one being a negative 0.04. Okay, so that's sort of the eigenvalue step in that process. So of course, now if we want to find the eigenvectors, we plug in our eigenvalues each time into A minus lambda I. And if we do that for, this is the lambda equals 0 case, so you're just getting the coefficient matrix exactly. And of course, if we solve that system, we'll get that we get the relation that x is equal to y, essentially, so we'll get a vector of 1, 1. Okay, and then for our second eigenvector, of course, this is the lambda 2 equals negative 0.04 case. And this will be when we plug in 0.04 and solve this system, we're going to get that 0.02x is equal to negative 0.02y. So essentially we get x is equal to negative y. So then our second eigenvector will be 1 and then negative 1. So now again, remember our solution form. We assume that this was a vector x times e to the lambda t. So of course this is for lambda 1 v1. So if we plug this in, we get that one solution is our eigenvector. So this is the x vector, and this is e to the lambda 1, which is 0 times t. So of course that's just 1, and we'll get that one solution is just 1, 1. All right, and then by similar logic, we'll get that y2 is equal to our eigenvector 1, negative 1, but then we need the e to the negative 0.4t since that was our other eigenvalue. Right, so of course we can use the superposition principle in this case, and we can say that a general solution is C1, right, at any arbitrary constant times our first solution 1, 1, and then an arbitrary constant times our second solution, which is the 1, negative 1, and then the e term there. All right, so this is our general solution. So now we can use our initial condition, right, which again, this is all depending upon the information where they told us that tank 1 was pure at first, at that tank 2 had 150 pounds. Right, so at time 0, y1 doesn't have any fertilizer, so that's y1 of 0 equals 0. And for our second tank at time 0, we started with 150 pounds, so that's y2 of 0 is 150. So now if we plug in 0, right, into both of these, right, we know that in the y1 component, right, we're going to get that this is equal to 0. And in our y2 component, we know that we get 150, right? So we get a sort of vector of equations here, right? So, and again, this is just plugging in 0 for t here. So that's why you're not seeing that, right? So then it just becomes C1 plus C2, which of course is equal to 0 because that's the y1 tank. And then you get the second equation, which is C1 minus C2 equals 150 for the y2 tank. So in equation form, we're ending up with this system of equations here, which you can solve fairly easily using elimination. And of course, you get that C1 is 75 and C2 is negative 75. Right, so that allows us to get a particular solution, which is just going to come from just plugging in for our arbitrary constants, just as we did before. So we get a 75 times the vector 1, 1, minus a 75 times the vector 1, negative 1, and then times that e to the negative 0.04t. And of course, you can write this in equation form as y1 of t equals 75 minus 75 times that e to the negative 0.04t. And then y2 is the same thing, except you're just adding the 75 there. Okay, so, okay, what does this all mean? So again, we were concerned with, we want to know when tank 1 has half of the fertilizer amount of tank 2. Remember, that was the original question. Right, so now the 150 pounds of fertilizer is always going to be there, right? So we need the amount in tank 1 plus tank 2 should always be 150. But then this is the relationship that we care about. This is when we want to know that half of what's in tank 1 is in tank 2, or that you could say you need to take 2 times what's in tank 1 to get tank 2, right? And if you solve that, you get that T1 is equal to 50 and T2 is equal to 100, right? So now if we solve this, well, Y1, right, we want that to equal 50. We want to know when Y1 is equal to 50 because that's when the amount of fertilizer in tank 1 will be 50 pounds. So if we solve that, right, you're eventually just going to solve that e to the negative 0.04t is equal to 1/3, which is going to allow us to get to the t equals 27.5. Okay, and then of course, so once you get t is equal to 27.5, that tells you that it will take 27.5 minutes for the amount of fertilizer in tank 1 to be half of what's in tank 2, right? And I just want to go back up to the graph here at the top here, right? And that's what you're seeing here, right? So they indicate here that when you have this 27.5 value of t, that's when you have y1 corresponding to the 50 and y2 corresponding to the 100. And right, this long-term limiting behavior does make sense because you would expect that after a sufficient amount of time, the amount of fertilizer in the two tanks would get pretty close, right, to about 50-50, which in this case would be 75 each, right? So that's an interesting example here of an application of systems of ODEs in a model here, right? Okay, so let's look at another example. So in the second example, we're going to look at an electrical network. So in this case, we want to find the currents for I1 and I2 in this electrical network as shown, right? So the I1 is sort of your current on the left part of the model, and your I2 is the current on the right side of the model. All right, and of course, for some initial conditions, we're going to assume that all currents and charges are zero at time 0, and we'll use that later later on in the problem to get our arbitrary constants. Okay, so of course, step 1 would be to obtain the model, and this is something that I wouldn't expect anybody to know how to do. This is just going to be a derivation resulting from Kirchhoff's voltage law. And since we're not in an electrical engineering course, we're just going to basically just come up with the model, and then we'll talk about how to solve it. Right, but it can be shown with Kirchhoff's voltage law that if we let I1, of course, again, be the current in the left loop and I2 be the current in the right loop, you can show that your I1 prime is given by this model, and you can show that your I2 prime is given by this model. Right, so what I want you to notice here is that you sort of have these constant terms here, which is going to result in something like this, right? So now we have a matrix equation where if we let J, and I just do that for notation's sake, I don't want to use I because we use that for the identity matrix. So if we let J be our vector of I1 and I2, and our A be our coefficient matrix, then this G is sort of like a non-homogeneous term. All right, so we'll have to approach this a little bit differently than we did the tank problem because now we have sort of this non-zero homogeneous term. Right, so of course, if you wanted to sort of spell this out as a matrix equation, we get something like this. All right. Okay, so that's what the model looks like. Now, since we have a non-zero G vector, of course, as we mentioned before, this is a non-homogeneous system of ODEs. Now, the idea is that we're going to use a similar approach, right? So what do I mean by a similar approach for what we did for a single equation? Well, what was the first thing we did for a non-homogeneous single ODE? First, we find a solution for the homogeneous version. And then we'll find a particular solution for the non-homogeneous version, and then we'll combine them to get our general solution. All right. Well, if we want to solve the homogeneous version, that's just setting your G vector equal to 0. All right, so then your system becomes sort of like the previous example where we had that tank problem. Right, so just as before, we're going to assume that our J is some x times e to the lambda t, which, as you might expect, just as before, is going to boil down to solving an eigenvalue problem. Right, so now if we find the eigenvalues and the eigenvectors of our coefficient matrix A, we're subtracting, again, lambdas on the diagonal. And if we find this determinant, you'll eventually find that you can factor as a lambda plus 2 times a lambda plus 0.8. So of course that indicates that we have that lambda 1 is -2 and lambda 2 is -0.8. All right, now for time's sake, I'm not going to go through and find the explicit eigenvectors. I'm going to assume that you know how to do that at this point, but you should verify that these are correct. All right, and another thing that I should mention here is that remember, your eigenvectors are only unique up to constant multiplication, right? So I just as easily could have made my V2, for example. I know a lot of times you could have also said, for example, that V2 would be like 1 and 0.8, right? A lot of you like to have a 1 in there for sure, right? Now that's totally fine to use as an eigenvector. That's just going to change your constant values later, all right? Well, your C1 and C2 values, but it will all sort of work out regardless of how you chose it. It will work out to be the same at the end. Okay, but anyway, if I use the V1 and V2 that I have here, then your general solution for the homogeneous system looks something like this, right? So this is sort of the same setup as the tank problem, where you have your constants times your eigenvectors times your e to the eigenvalue terms. Okay, so of course now part 2 is we need to find the particular solution based on our non-zero homogeneous term, all right? Now since our vector of non-homogeneous terms is constant, we're going to assume that our particular solution is a constant column vector, all right? So we're going to assume that our particular solution is a constant column vector. All right, and now the nice thing about that is that if you take that derivative, then you get a 0, right? So now your system that we had before, our j prime equals a times j plus g, is going to become 0, right, on the left-hand side, because that's your derivative, is equal to your coefficient matrix A times a constant column vector A, right, plus your non-homogeneous non-zero G vector. Now, if you write this out in system form, right, so this is just taking the coefficient matrix A and multiplying it by this A1, A2 vector and adding it to G, we know that that has to equal 0. Now, of course, this is going to allow you to solve for A because you have 2 equations and 2 unknowns. And if you do that, you'll find that your A vector would have to be a 3, 0. All right, so that's going to allow us to get our general solution, right, which again is going to be made up of your homogeneous version, which we found earlier, right, this J sub H here, and then our A vector, which we just found, was 3, 0. Right? So now we can write this out in equation form as follows, right? So putting this all together, we have 2c1 times e to the negative 2t plus 5c2 e to the negative 0.8t. And then the constant in this case was the 3. And then in the I2, you don't have you adding 0, so we usually don't write that. And then, of course, you have the c1 e to the negative 2t plus 4 c2 e to the negative 0.8t. All right. So now the final step in this is that we want to find the initial conditions. Well, we want to find our arbitrary constants based on the initial conditions, right? And this was coming from the fact that we assume that all charges are 0 at time 0. So this is going to make life a little easier. So now if we plug these into our I1 and our I2 equations, we get the following system of equations, which you can solve again fairly easily. You can find that C1 is -4 and that your C2 is 1. So now if we plug this in to our solution, we get something like this in our vector form, which is going to allow you to say that your initial condition, or sorry, your current equations are given by this system. All right, now one thing that we'll mention here, but we're not going to delve into too much, we'll just sort of mention it in passing here, and that's that you can represent this in two separate ways, right? So this first graph is showing I1 of t and I2 of t both against time, right? So you're seeing two separate curves on that first graph there. Now in the second graph, we have a parametric equation, right? So this is, we're plotting I1 versus I2, and this is sort of a parametric equation. Well, it's not sort of, it is a parametric equation, right? And this direction arrow here indicates the direction of time, right? Now, it turns out that this second graph is usually the much more important one that we care about in sort of this analysis here, right? So now this curve here, just for some vocab, this is typically called the trajectory, right? And of course, this I1 versus I2 plot is also known as the phase plane here, right? So it's possible that in a future video we'll sort of talk about this, but this gives you, actually, it turns out that the second graph is much more useful. All right, so that is something that we do want to mention. Okay, now one last thing for this video that will be sort of a tangible skill that we'll need moving forward regarding our systems of ODEs is converting any nth order ODE to a system of first order ODEs. All right, so now this is something that happens a lot, particularly in research regarding higher order ODEs, because it's generally easier to solve a first order equation, of course, than an nth order equation. So what we can do is convert that nth order ODE into a system of first ODEs, right? So if we're given some nth order ODE, so this is just a fancy way of saying that you have an nth derivative on one side of an equation, and the other side is lesser order derivatives, right? And it's some function of that, right? Now, if we set our ODEs, set our derivatives ordered in this way, if we set y1 equal to just the function y itself, y2 is equal to the first derivative, y3 equal to the second derivative, and etc., then we can form a system where the first n-1 equations will just be sort of going on to the next one, right? So this is all found from example. We know that y1 is equal to y, and if you take the derivative of both sides, you're going to get that y1 is equal to y prime. But what is y prime? From the second equation, we're told that y prime is equal to y2. So this allows you to say, with this information, that y1 prime is y2. All right, which is what our first equation is in the system, right? And you can do that as far down as you want. And then the only difference here is that your yn prime, so this is basically the original ODE, but now you've replaced all of your derivatives by using star. All right, and this is a fairly common skill, especially when it comes to analysis of higher order ODEs. All right, so we're going to do an example of this. So in a previous video, we discussed the ODE, the second order linear ODE for the unforced damped mass spring system, and we had an equation that looks like this, right? Now, if we want to work with it as sort of we demonstrated in the video, or sorry, not in the video, in the example above, we want to make sure that our y double prime is solved explicitly. And so if we do that, you can move your divide through by m to get your y double prime coefficient to be 1, and then move the other terms over to the other side, right? So again, as we mentioned before, we want to set y1 equal to y, and y2 will be equal to y prime. So then our system will become, well, y1 prime is equal to y2, right? And again, y2 prime, which is y prime prime, which is just y double prime, is equal to negative k over m y1, because that's y. And then we have negative c over m times y2, because that's y prime, right? So maybe we'll note that here. This is y, and this is y prime, and this is y double prime. So this is the same equation as the original, except we've replaced our y and our y prime with their respective y1 and y2. So now if we want to represent this in matrix form, right, again, with your vector y as your solution vector, then you have a system that looks something like this. All right, and of course, how do we solve something like this? We've shown it a couple times now that this is just equivalent to solving an eigenvalue problem. All right, so if we do that, we find the determinant of our coefficient matrix with lambda subtracted on the diagonal. And then you can show that your characteristic equation is this, right? Which is what we'd expect. This is what we would find if we were to solve this without using a system, right? If we just assume that our solution was e to the lambda t or whatever, right? So same thing happening here. Now, for computation's sake, we're going to pick some tangible numbers for m, c, and k here. All right, we're going to let m be 1, c equal 2, and k be equal to 0.75. So if we do that, our characteristic equation is now this. So we can factor that as a lambda plus 0.5 times lambda plus 1.5 is equal to 0, which gives us these two eigenvalues. All right, so you can go through and you can verify that these are the corresponding eigenvectors. So for v1, you get a 2, -1, and v2, you get a 2, -3. So then this is our general solution here. Right, and of course you can represent that in matrix form as this matrix here. All right, and if you wanted to, you could also represent it in equation form as well. Now, of course, we weren't given any initial conditions here, but if we were, you could then take this further and you could solve for C1 and C2. Okay, so that wraps up this video on sort of an introduction to systems of ODEs as they pertain to models in engineering. So I hope you enjoyed the video, and I will see you next time.